Well, hello, I'm Abhishek DAHIYA, and first of all, I would like to thank the organizing committee for inviting me or for giving me this opportunity to present our research work to this virtual event. And so today I will present our work on stretchable strain sensor for human movement monitoring. So most of the work is carried out in University of Montpellier, CNRS Laboratory, IES, and LERM. And part of the work is also done in collaboration with University of Glasgow. The motivation behind this work is to basically realize the concept of Internet of Medical Things. So this concept has range of applications such as patient monitoring through medication centers such as hospitals or private clinics and so on. So as you can see in the slide here, so it has this smart wearable sensor which is put on a human body to basically monitor or to store or to sense basically the important vital information uh, such as blood pressure, respiration, and so on. So this is done by this smart wearable patch. So it's an energy autonomous wearable sensor. So as you can see, it has four major blocks. So one is a sensing unit, which can be a strain sensor to monitor your respiration, a chemical sensor to monitor a glucose or such kind of such as cortisols, for example, from your sweat. And there are other blocks basically which are needed to process this information and power supplies such as thermoelectric generator which can take the energy from the body heat and can power this sensor, and finally a communication system which will send this process information to outside world through the low power Bluetooth, and this set of information can be sent to the cloud for computing where there is already online programs prepared by medical expert, and they will compare this set of sensed parameter of a patient, and if case of emergency this information can be moved on to the or passed to the hospital which will take appropriate action. So this work we are focused on to develop a wearable sensor. So to be a wearable sensor, it has some set of characteristics which will satisfy it for a wearable application. For example, stretchable. So it has to be stretchable in a way that it can conform the human body. It has to be highly sensitive to have a higher signal to noise ratio. So basically, a higher gauge factor. It should be low power so that the energy which is scavenged through a body heat or solar or so other mechanism can power it. And there are some other characteristics such as it has to be biocompatible, it should be conductive, it should avoid the moisture and other and external things to affect the measurements. Among variety of sensors, mechanical sensor which are available, piezoresistive sensor have gained a lot of importance. Why? Because it's a simple, it's very easy to fabricate, and there are simple readout circuitries available, and they are low cost. So among various approaches available in the literature, there are two which we found are gaining a lot of importance. One is the metal crack-based sensors, where the metal films have there are cracks which are controlled in a way, and a slight strain into these cracked metal films, you can have a very high gauge factor or basically very high sensitivity. So some reports here there where there is almost 2000 has been achieved. However, the problem in this sensor is basically they have a very limited stretchability. So they can work something like 2 to 10% or max 20% of in the sensing window basically. And the other approach here you can see is basically where there is a conductive path is made by percolating a one-dimensional material in a polymer. You can see here, and this approach has basic advantage that the sensing window is huge, and you can stretch up to 200 to 300% of these devices. However, the gauge factor, the sensitivity of these sensors are basically in a moderate range, something like 10, 50 or some bit higher, but not as high as a crack-based approach. So, based on these motivations, here is the outline of the present talk. So we have made a process. We have basically used a micromolding-in-capillary process, which is well known to make this strain sensor, stretchable strain sensor, and two kind of filler materials being investigated in this approach. So this is carbon nanotubes and silver nanowires. So I will present the electromechanical characterization results, what we have done, and also we will present some real-world application based on these sensors. Finally, I would like to conclude our work, in the conclusion section. So here is the slide showing basically the steps what we follow to realize our strain sensors, stretchable strain sensors, using a micromolding-in-capillary process. So in this beginning, the step one, what we have done is basically we have made grooves or channels in a soft polymer. So we can use a variety of polymers such as PDMS, EcoFlex, and in this work we are showing the results of dragon skin. It's also a typical soft polymer. So these grooves or channels are easily made by a standard molding process. And in the second step, what we have done is basically we drop cast the 1D material solution, which is separately prepared in ethanol or IPA in alcohol solutions. And the rate of basically due to the capillary forces, the film is self-aligned. The nanowire film, basically percolated film is self-aligned, and then we in the third step we put silver epoxy on the two ends, and the last step basically we package all the device in the second layer of dragon skin. Here is a typical macro channel device you can see here. So the channel width, the size dimension basically we can control by the we can easily control by the mold or SU8 polymer or Captain tape, whatever we have used. For example, you can see here we have miniaturized channels in this slide, and we are showing by optical micrographs that these devices are quite stretchable, twistable, and foldable. And you can see the channels are not, damaged while doing stretching or this kind of mechanical deformation. So here is the cross-sectional device, cross-sectional SEM image of the device, showing the dispersion of this 1D material in a polymer. So you can see, although not very clear, but here there is a separate multi-volt carbon nanotubes inside the polymer, which is difficult to achieve. But however, with the optimization of this process, we can achieve it quite easily. And the nominal resistance graph showing on the bottom right here, you can see a typical very low nominal resistance value of around 100 ohms can be achieved using silver nanowire, and using multi-volt carbon nanotubes the values around 1.2 kilo ohm. So let's start with the results. Here is the electromechanical characterization results of CNT devices. So here is the test bench. So it's a very simple. A piezo motor is basically used to strain our sensors, and there's a lab view control kitlet to monitor the change in resistance. And here is in this graph you can see we are checking the performance of the device. So here you can see the displacement in millimeters. So here is up to 1.8 centimeter or 18 millimeters we have stretched, which is corresponds to 180% of the strain, and at this the gauge factor is around 60 maximum we have reached. And the interesting thing, while recovering the device, we comes back to the original nominal resistance, which is very interesting. That means there is almost no hysteresis in these devices. The other thing is we have also done the effect of the strain rate. So how you are stretching these devices, and you can see the faster you stretch, the the faster you can get the response. So basically, these devices respond very fast for less than 1 second. And this is the graph showing with different strain we have tested the change in resistance. So you can see the sensing window is quite large and quite sensitive. So 2% of strain we can sense, and here is the 64% strain we can sense. The other test what we have done on CNTs is the stability test, which is also important to see how robust these sensors are. So here in the two conditions we have tested almost for more than 20 hours of continuous operation. There is a 30% of strain at 0.1 millimeter per second, and it is 40% of strain and at 5 millimeter per second. And in both these testing, which lasted up to 20 hours, which correspond to 900 stretch cycles in the first case and 6,000 stretch cycles, which is a very heavy strain device, and we can see that the performance doesn't degrade. And also after finishing this test, the device remains into the nominal resistance remains the same. So we can say that they are really highly robust and devices, but the gauge factor is in moderate around 50. On the other hand, the silver nanowire devices, they are very sensitive. So basically, you can see here the change in resistance is very huge. It's 10 raised to power 6 orders, and which corresponds to a very high gauge factor. And the mechanism behind this, as we have already discussed, is the cracks which are appearing because of the brittleness of the silver nanowires. Here is the graph to show the sensitivity, the gauge factor of more than 10 raised to power 6, which is one of the best in the literature. The stability test we have done, so we can see that up to 100 cycles that these sensors, these devices, silver nanowire based devices can sustain. So here is the values extracted from this graph. So you can see the on state or you can say the off state basically. So here it's quite stable, and here is in the on state where it's conducted. So we can conclude that it's high gauge factor but a moderate robustness from these devices. So here are some real world applications we have done. So in all this demonstration, we have used multi-volt carbon nanotube device because of its robustness. So in the human body, we can have some subtle movements during respiration, or we can have higher strain also while moving fingers and so on. So in the first case, we have monitored the finger movement. You can see while 45-degree bending, 90-degree bending, there is a significant amount of change in the resistance, and it's recovered back while the finger comes back to its position. Then there is an artificial knee movements. We have monitoring the angles, wrist monitoring, and also the respiration. So here is the graph showing the normal breathing and deep breathing. So you can see when the person starts to breathe heavily, you can see the difference. In the real world, however, we need some science to transfer this change in the the aspiration, or basically the movement. So here we have developed a circuitry basically which is light sensitive or LED strain sensitive LEDs, which will change its colors depending on the strain. So here there is a green which is in the low strain, and the red is where is highly strained. So in the video you can clearly see, for example, yes, so there is the finger. You have a sensor on the finger, and when we bend, there is the light, the LED lighten up. So more the LEDs you can see, the more the strain the device is. There is another application which is not for human monitoring, but for basically for soft robotics. This sensor can find applications. So this is the work done in the with the University of Glasgow in collaboration. So where basically we are controlling the teleoperation of soft robots. So this is a robotic hand we have made using 3D printing, and these are the sensor we have put on a human hand, and you can control the robotic, basically the operation, using these sensors. And this is the real monitoring of the change in resistance you can see when we have bended our fingers. So this shows that this sensor responds very fast, which we have already seen before. The sensing, basically the time is quite low, and they are highly sensitive, not highly sensitive, but very robust device, which says, but we do moderate sensing. So to conclude our work here, so what we have shown that we have fabricated this highly stretchable sensors using a simple mimic process, which shows that we can reproduce these devices without any heavy and costly equipment. So it's a very low cost approach to make this stretchable strain sensor using CNT dragon skin composites. We have seen that the devices are quite robust, and they have stable performance, but the gauge factor is moderately high, 50, which is of course higher than the current state of the technology, which is around for metal base, which is around 5. So silver nanowire dragon signal on the other hand showed very high gauge factor, 10 raised more than 10 raised to power 6, but with moderate robustness. So after 100 cycles, the device starts to show some degradation. The CNT dragon skin basically used, we have shown to monitor the subtle and large strain movements. And the next step is now to co-integrate the energy autonomous into the energy autonomous variable sensor, basically. So this is the project with Smart Vista, where we are developing thermoelectric energy harvester to power these sensors. So at last, I would like to acknowledge the Smart Vista project for providing the funding to carry out this work, and thank you very much. And I would be happy to answer your questions. Thank you.